So here we'll talk about an introduction to linear systems, and this is in section 8.1, where we're going to look at systems of linear differential equations. When we look at models, oftentimes they contain equations that are of order greater than 1, so second order equation, for example. And in the case when they are linear, we actually can write those as systems of as many linear differential equations. So now when we have more than one linear differential equation in more than two variables or two or more variables, then we have a linear system of differential equations. For example, here is a system of differential equations in two variables, x and y. And now we see that we have two equations. The system can be written in matrix form, and what this constitutes is we take on the left-hand side and we replicate what is on the left-hand side of the system, which is x prime and y prime. On the right-hand side, we replicate what is on the right-hand side in this system. And basically in order for us to write this matrix that I've written here, you allow the first column to correspond to the first variable, in this case x, and the second column to correspond to the second variable, in this case y. And then I have the column vector of variables x and y. In the same way that we can write the system as in matrix form, we could write a matrix form system into a regular system. So we could go back and forth in this way. Something else that we're not going to focus on, or I'm not going to ask you to do, but I want you to be aware of, is that if I have a linear differential equation of any order, say in this case of order 2, I can write it as a system of linear differential equations of as many equations as I had the order. So if I had second order, then I will have 2 linear differential equations. If I had third order, I'd have 3 linear differential equations. You can see how it would be very important to know how to deal with these systems in matrix form, because in a way I can then understand how to solve and understand the solutions of high order differential equations, linear differential equations in general. So a system of linear differential equations we're going to be these systems we're going to be looking at are going to have this form: x prime equals ax plus f. X prime is the vector of variables where I've taken the derivative, a is some matrix, x is the vector of variables, and then f is a optional vector that may be present. Now if it's not there, then we say the system is homogeneous, and if it is there, then it is some vector, as you can see here, of functions that depend on t only, so x and y, or the two main variables do not appear in f. So there are two things that I want to highlight. The first one is a solution. So if I have a system such as this, then I would say that a solution is a vector that satisfies the equation, meaning that if I plug in that vector here for x prime and I plug it in for x, then this equality sign is satisfied. Here's an example. If I have this system, and I've written it in just regular system form, and suppose that I'm asked to verify that this vector x is the solution to the system. Well, what I have to verify, first of all, I can see here that if I multiply times e to the minus 5t, I get exactly this vector. So I'm asked whether this vector satisfies that equation. In this case, really what I'm saying is that if I let x be e to the minus 5t, and I let y be 2e to the minus 5t, then each of these two equations will be satisfied if I check. Find the derivative of x, put it here, 3 times x minus 4y, the equal sign should be satisfied. Same thing with the second equation. Now, finally, we also can talk about the same theory that we talked about earlier. So if I have a system of n linear differential equations, or the same, if I have a system with an n by n matrix or n variables, then if I have a set of n solutions, that set will be a fundamental set if it is linearly independent. So two things are satisfied. I have n of them, and it's linearly independent. And if it is, then I can also write the general solution in this form, where just like before, I take C1 times the first solution plus C2 times the second solution, and so on.